Alrighty, so I'm going to run through pretty much the whole package of notes here about properties and laws of logarithms. All right, let's see. So the first little definitions of logs are right there. The argument has to be greater than 0, and the base also has to be greater than 0, but not equal to 1. And then we have this little quirky couple of properties here about logarithms, numbers 2 and 3 there on the screen. I'll let you copy those down. Don't want to say too much about them at this point. They're just kind of like an odd little thing of the kind of circular structure, I guess, of a logarithmic expression. All right, so we're going to move into these laws of logarithms here. The first one is called the power rule. We spent pretty much a day just looking at this. Log base b of x to the n power could be written with that exponent n there as a coefficient, n times log base b of x. This is you can write both of these expressions are valid, and so if you've got a logarithm with an exponent on the argument, like log base 2 of 3 to the 5th power, you could write it as 5 times log base 2 of 3. You can go the other way also. Here's a couple of those. If you had log 1/2 times log of 5, you could write that as log of the square root of 5, because 5 to the 1/2 power is the square root of 5. Or 3 times log of 4 could be written as log of 4 cubed, or you could write it as log of 64. So once you start learning all these different little things about logarithms, they can be written in lots of different correct ways, just kind of according to whatever you're trying to do with that logarithm. The power rule is one of the most important, I think, laws of logarithms because it allows us to solve exponential equations. So we'll do a couple of examples of that. Here's the first one. Very simple, kind of uncomplicated exponential equation. 12 to the x equals 95. And just for visualizations here, if you had imagined a graph, y equals 12 to the x, it might look something like that purple curve up there. It's an exponential curve. It's got an asymptote there on the left side, and at some point it starts to really ascend rapidly. At some point it will go through the y value of 95, and what we're trying to do is to find that x value that makes that happen. So we're solving the equation. That's one way to think about solving an exponential equation. And the new trick that you're going to learn here by doing this is to take the log of both sides of the equation. All right, that's the new thing, is take the log of both sides of the equation. It's just another thing that you can do with an algebraic equation, is take the log of both sides. That exponential part has to be isolated first, and that's how we started on this one, so just want to point that out. So when you take the log of both sides, that just means log of 12 to the x equals log of 95. So now we get to use the power rule and bring that exponent of x there all the way kind of down here. This is why some people call it the wraparound rule. Now it's x times log of 12 equals log of 95. And to isolate x, that is to solve for x, all you have to do is divide by log of 12. So there's your answer there. X equals the log of 95 divided by the log of 12. That fraction is what we call the exact value of x. It's not always the most practical value or useful or kind of illuminating, that's a better word, illuminating value. It doesn't tell you what it means all the time. So it's good to be able to do that on a calculator. So I wanted to demonstrate using a calculator to do that. It's very important that you're able to do this. Here's a calculator. And let me clear that stuff out. We're going to take log of 95. So log of 95. Notice the parentheses are closed right there. I'm going to now divide that by the log of 12. And so I get this number right here. 1.833 would be a good way to round that off to 3 places. So make sure you're closing the parentheses around the argument before you hit the division button on your calculator. It's a really important little detail and an easy one to make to mistake. All right, so back to the notes here. There's our approximate value. And here's another one that's not quite as uncomplicated. It's still not very complicated equation. This was one of the problems where somebody in a math problem was trying to save money, I should say, and they were doing that by starting with $3 and then doubling that every month, and they had kept aside a $20 bill kind of as an extra amount. So there's the equation. S of x dollars equals 3 times 2 to the x plus 20. And the question that I posed was, well, how long would it take under that plan to reach $1,000? So if you set that equation there, that equal to $1,000, and then solve it, and notice what we do first. We subtract the 20, and then we divide by the 3, and so then we have this 326.6 repeating equals 2 to the x. Now we can take the log of both sides. So make sure that you isolate that exponential part of the equation completely before you take the log. All right, and then it's the same routine that we just did. We're going to take the log of both sides, use the power rule to move the exponent down as a coefficient of log of 2, and divide by log of 2, and there's our exact version there, that fraction. And once again, that's not a very practical answer to the question, how long would it take to get $1,000? So you do need to use a calculator, and it works out to be about 8.3 months. Okay. So another couple of laws of logarithms here, very important to go through. The second one that we'll call that the product rule. And that rule looks like this. It's log of A plus log of B could be written, if necessary, as log of AB, log of A times B. Important to point out that the logarithms have the same base. That has to be true. And so this is just a way that you can simplify a sum of logs and writing them as the log of the product of their arguments there. So in other words, log of 3 plus log of 7 is just the same thing as log of 21. Those are equal to each other. You can start with one and get the other one, and it doesn't really matter which way you go. You can, like I say, you can combine logarithms together this way, or you can split them up. Log of 5x, well, 5x is a product, so that could be written as log of 5 plus log of x. It just depends on what you want to do. So we're going for fluency here and being able to write things in different ways. Here's another one, log of 30. Well, 30 is 3 times 10, so I could write that as log of 3 plus the log of 10. It turns out, though, keep in mind then, log of 10 is equal to 1. So I could write that log of 30 as 1 plus the log of 3, if that was somehow useful to me. Kind of extending that idea again, this is how logs were used in a lot of ways. Log of something like 237. Well, 237 could be thought of as 100 times 2.37. So I could write that log of 237 as 2 plus log of 2.37. So look out for powers of 10 showing up in your work, or maybe places where you could use them. And does it simplify the expression? Well, I don't know. Somehow it might make it more useful in some way or another. All right? This is, like I said, more about fluency than anything else. Logarithms are used in a lot of different contexts, so it's good to be able to use them in different ways. The other log law that we're going to look at there is called the quotient rule. It's kind of the inverse of the product rule. So log of A minus log of B, so we're subtracting two logs. You could write that as log of a quotient. Notice which one is on the top, A divided by B, okay? So log of 16 minus log of 2, 16 divided by 2 is 8, so that's the same thing as log of 8, all right? The same thing is true in other things, though. I mean, if you had log of 5, you could consider 5 to be a quotient of 10 divided by 2. So you could write that as log of 10 minus log of 2, and that's 1 minus log of 2, because log of 10, once again, is equal to 1. So these quotient rule and product rule laws of logarithms can be combined in different ways, and we'll get lots of practice of that over the next few days. I wanted to point out first, though, a couple of common mistakes that people make. Please look at these carefully. First one here, log of A minus B equals log of A over log of B. No, that is wrong. All right? So that is a very common mistake that people make. All right? Make sure that you observe what that quotient rule actually says. It's not log of A divided by log of B. It's the log of A divided by B. All right? It's a single log there. Okay? Another one, log of A plus log of B equals log of A plus B. no, I certainly understand the temptation to use that, but that is just simply not true. In fact, the log of a sum, like log of x plus 2 down here, that cannot be simplified. In fact, all right, so there's just nothing you can do with that. That doesn't really simplify or expand in any way at all. So that's wrong also. And then another common mistake that I've seen over the years is something like log of a divided by log of b equals a over b, as if the logs kind of cancel each other out. No, 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 that does not work. That doesn't actually make any sense at all. So make sure you don't do that one. All right, let's see what else we got here. Yes, the last thing in this little batch of notes about logarithms is this thing called the change of base rule. The change of base rule is a way to rewrite any log expression in terms of any other base that you want to use. Frequently, we want to use base 10 simply because our calculators like base 10 and they can calculate logarithms using base 10 logs. But it could literally be any base that you want. Here is what the change of base rule looks like in its kind of abstract, generalized form right there. I won't read it. You can read it. The C on the right side there, that could be that's the new base, log of any changed base. So log base B of x is log base C of x over log base C of b. Notice that the b, the base of the log, and stays on the bottom, stays in the base. Okay, say it that way. And the argument goes up here. All right, so log base 3 of 7, you could write that with base 10 logs, log of 7 over log of 3. And it also works, the change of base rule also works with writing functions. So let's say you had the graph, or had to write the equation for log base 3 of x plus 4, y equals that. Well, if your calculator or your graphing machine didn't like log base 3, you can still write this using the change of base rule. You would just write it y equals log of x plus 4 divided by log of 3. All right, and then finally, the last thing I want to do is kind of connect a couple of ideas here. This change of base rule has a big connection with solving equations. So here's an equation, 2 to the x equals 3.6. I just made up a couple of numbers there. So one of the things that some people are learning to do is to take an exponential expression like that, or equation like that, and rewrite it as a log equation. So you might want to do that. So you could take this equation, 2 to the x equals 3.6, and put it in log form, noticing that the base is 2, right? 2 to the power of x. So you're going to have log base 2. And the exponent is x, and the argument is going to be 3.6, sorry. So it's log base 2 of 3.6 equals x, all right? In a sense, we've just solved the equation for x. Now it's log base 2 of 3.6 equals x. If your calculator can handle that, then you've done all the work that you need to do to actually solve that equation for x. However, if you don't have a calculator that can do that, and you'd rather get the more kind of proper ratio of logs, you would do what we did up above here, which is to take the log of both sides. Log of 2 to the x equals log of 3.6. And then you would use the power rule, and you would get this x times log of 2 equals log of 3.6, and divide by log of 2. And so isolate x this way, log of 3.6 over log of 2. All right, well, that's cool. Also, when you think about using the change of base rule for this logarithm right here, all right, so log base 2 of 3.6, that can be written using the change of base rule and using a base 10 log as log of 3.6 over log of 2. Well, there it is again. It's the same thing. That's just what we got right there. So the change of base rule is like solving kind of an uncomplicated exponential equation like that. They give you the same ratio. All right, that'll do it for notes for here. I'm going to post this video and just a PDF of all these slides in the forum.